Alrighty, good morning everybody. Welcome back to Calc 1. Plan for today is I have a quiz for you on Standard 6, and then we're going to talk about the chain rule. Got my next office hours are going to be on Monday, the usual times, 11 to 11:45, and from 2 to 3. As far as homework goes, homework 9. As I mentioned at the end of last class, is now going to be due Wednesday, and will be over the chain rule, which we're going to be talking about in great depth today. Also, first exam next Friday. So, exam. How does that work? So if you remember, each exam is basically going to be like a bunch of quizzes stapled together. So this first exam is going to basically be like, pretend I took a standard 1 quiz, standard 2 quiz, all the way up through standard 7, stapled them all together. And you'll have the full class on Friday, 65 minutes, to earn as many masteries as you can. So this is kind of an opportunity for you to earn potentially a bunch of masteries all at once. And I'll be sure to I'm going to update everyone's mastery totals on Canvas over the weekend, so that you know how many masteries you have going into the exam. If you have 2 masteries in something, I encourage you to leave that question blank on the exam. You do not need a 3rd mastery. It will not give you extra credit. You can skip it. So if you come in and you maybe only need to do like 3 or 4 questions, potentially, if that's true for you, then congratulations. Or you could do all 7. 1 sheet of notes, front and back, you are allowed to bring with you into the exam. Whatever you want written on them. Don't try and type out the entire packets in like size 4 font. That will make me sad. If you want to put like example problems, state some theorems on there, that might be helpful. That could be helpful for you. Any questions or comments about the exam next Friday? Yes.
So each standard will be labeled. This is standard 2.
Yes. Yeah. It'll all be in order, and each page at the top will say like standard 1, standard 2, etc. Should be clear when you're taking the exam which questions correspond to which things. Yes, Carly?
Do you have objections to us writing like an example problem on the sheet? Like if we mess something up on a quiz and then we wrote that on a page of notes, is that okay?
You are welcome to write whatever you want on your sheet. Just don't break your way into my office and write answers to the exam ahead of time. But yeah, if you want to write out some sample problems, some examples of like old quiz problems, I think that would certainly be something that could be helpful for you to have on your sheet. Other questions? Alrighty. What do mathematicians wear to keep the sun out of their eyes? Keep the sun out of their eyes. Mathematicians wear the visor. Okay. Also, just so you're prepared. If we don't, I plan on having a standard 7 quiz next Wednesday in class. Probably not on Monday because I'm not sure we'll finish it today, but next Wednesday we'll have that quiz. Alrighty, and with that, time for the standard 6 quiz. Go ahead and take a few seconds to finish up your thoughts. And pass your quizzes forward, please. Pass your quizzes in, please. Making their way down here. Okie dokie. So, one more.
Yes, that is right.
So, when we left off last class, we had started to talk about a couple different forms of notation for taking the derivative. We had seen Newton's notation for if you want to differentiate f of x, you just write it out as f prime of x. And if you prefer to use Leibniz's notation, you use this sort of df dx to say the derivative of f with respect to x. Or if you prefer, you could write it as d dx of f of x. Where writing this d dx out in front is basically saying take the derivative with respect to x of whatever's inside. And so last class we talked a little bit about the history of Newton versus Leibniz and the epic battles of calculus. And a little bit about why sometimes Newton's notation might be preferable because it's kind of simpler and maybe a little bit easier to look at and work with, versus Leibniz's notation can be advantageous in the sense that you don't necessarily need to have an explicit name like f of x for your function. You could just say, take the derivative with respect to x of 3x cubed plus 7 without having to give that function a name specifically. The reason why I choose now to talk about the two different notations for Newton's calculus versus Leibniz's calculus is it's going to lead into a discussion of our next derivative taking rule where we're going to have two different versions of the next theorem. One that's kind of uses Newton's notation and one that's going to use Leibniz's notation. So take a look at a function here. F of x equals square root of x squared minus 6x. Right now, I don't think we have the tools necessary to differentiate that as of the end of standard 6. Why is that? What is it about this function that makes it so we can't just differentiate it using the product rule, quotient rule, power rule, etc.? Okay.
You couldn't distribute the 1/2 exponent because it's subtraction on the inside.
Yeah, we can't really distribute this square root of x. We cannot say that that's equal to something like square root of x squared minus square root of 6x. If we could, then we could probably use the power rule and difference rule to make our lives easier. But unfortunately, we don't have anything like taking the product or quotient of nice things that we can use the power rule to differentiate. Instead, we have sort of two different things going on here. It's my eraser. We have a square root, and we have sort of this polynomial inside of our square root, this x squared minus 6x going on. And while we know how to differentiate the square root function, if it was just square root of x, we could write that as x to the 1/2 and then differentiate using the power rule. We know how to differentiate x squared minus 6x in the sense that that's just power and difference rules. You get 2x minus 6. The problem is we have two things that we know how to differentiate individually, but we don't yet have a way to kind of handle both of them at the same time. X squared minus 6x inside of a square root. And so our next rule, the chain rule, is going to help us determine how can we differentiate functions when we have multiple sort of things going on like this. When we have two expressions that we know how to differentiate each one individually, but it's harder to differentiate both of them when they're combined in the same function. So this is going to be called the chain rule. Chain because we're just going to end up looking at how can we chain functions together. So, like I said, this rule is going to have two different versions to it. First version is going to be using Newton's notation, the sort of f prime of x notation that we're maybe a bit used to. And what this rule says is that if we know that our function f of x equals g of h of x for some continuous functions g of x and h of x, then the derivative of f prime of x is going to be equal to the derivative of g prime of h of x multiplied by h prime of x, the derivative of h. Yeah. So let's take a look at what does that actually mean, because I think this is one of these theorems that when you first look at it, it doesn't really make much sense because it has a lot of moving pieces. So it has three different functions floating around, this f, this g, and this h. But once you kind of understand what all the different pieces are, you can just kind of plug and chug them into this formula here. So our original function is f of x equals square root of x squared minus 6x. And what I would like to do is find a way to write this as the composition of two different functions, some g of x and h of x. So as a reminder, what are we actually doing to our x here? We're plugging it into this polynomial x squared minus 6x. And then after we plug it into this polynomial x squared minus 6x, we're taking the square root of that whole expression. When you do the chain rule, and use the chain rule to help differentiate when you're doing two different things to your x's, in this case plugging them into our polynomial x squared minus 6x, and then plugging it into the square root, the g of x and the h of x that we're going to need to use are going to be sort of the inside, the h of x will be the inside function, the thing we're doing to our x's first, and then the g of x will be our outside function, so to speak. What's kind of the last thing that we're doing to our x. So as an example, if I were to ask you to take f of, f of 10, for instance. what are you gonna do first? Are you gonna plug 10 into x squared minus 6x first, and then take the square root of that? Or are you gonna take the square root of 10 first, and then plug square root of 10 into x squared minus 6x? Rachel? The first one, plug it into the x squared minus 6x? Yeah, I would say so, because the square root is sort of our outer function here. Here, the first thing that we're doing to x when we plug it into this formula is we take x squared minus 6x. And the second thing that we do is we take the square root of whatever we get when we do that. So here, when we think about our h of x, which is always going to be our inner function, where g of x is sort of our outer function, so to speak, our h of x is going to be the first thing that we're doing to our x, which is, in this case, going to be taking x squared minus 6x. What is our g of x going to be in this case? Sort of the outer function, the thing that we do to our x's after we plug x into x squared minus 6x.
Square root of x.
Square root of x, nice. Yeah, that's exactly it. Because if you were to plug your h of x, if you were to take x squared minus 6x first, then the g of x, the thing you're doing to x squared minus 6x, after you've done that, is to take the square root of that. You've taken x squared minus 6x, and now we're taking the square root of whatever that gives you. So in essence, we can say that our f of x is equal to g of h of x, which in this example means taking the square root of our h of x expression. And if our h of x is x squared minus 6x, that's going to come out to square root of x squared minus 6x, which it was our original function. So you may have seen this notation being used before, g composed with h of x. That's called taking the composition of two functions. I don't want to get held up too much on the notation here, but if you ever see this, that means the same thing as taking h of x first, and then whatever you get for h of x, you plug that into your formula for g. So in this case, our h of x, the inside thing, the first thing that's happening to x, is we're taking x squared minus 6x, and then in order to get, in this example, say, how do we get from x squared minus 6x to square root of x squared minus 6x? We have to take the derivative of the whole thing. Or we have to plug the whole thing into g. I'm getting ahead of myself. Meaning we take the square root of our h of x function.
So is g of x the square root of x or the square root of h of x?
Ah, good question. Vera, earlier you said you wanted your g of x to be square root of x rather than square root of x squared minus 6x. Why was that?
Because whatever h of x is, that's basically what we're going to be plugging in to g of x. I'm not sure if I explained that.
It's definitely a hard thing to explain. But I think what Vera's getting at is we want it to be the case that when we plug in our inner function to our outer function, we get back the original f of x. If we had said that our g of x was something like x squared minus 6x, then if we had plugged in our h of x into this function g, we'd end up with something like square root of x squared minus 6x squared minus 6 times x squared minus 6x, which is very much different from our original function. Because something to keep in mind is when you want to take g of an expression like x squared minus 6x, that means whatever your g of x is, whatever your outer function is, anywhere that you see an x in this expression, you're going to be plugging in the entire expression for your h of x. In this case, the x squared minus 6x term. And so when you take square root, and so our outer function is just taking the square root of this. So our outer function just becomes square root of x rather than square root of x squared minus 6x. It's a very subtle thing, and honestly, kind of choosing your g of x, in my opinion, might be one of the hardest parts of doing the chain rule, is keeping in mind that your outer function is only going to be doing something to your h of x. So we want square root of x here rather than square root of x squared minus 6x for our g of x. Are there questions or comments? So let's see if we can actually use this formula. Because I think once we know what our g of x is and our h of x is, the formula itself isn't so bad. So in this case, we have an inner function. Our h of x equals x squared minus 6x. And an outer function, which is g of x equals square root of x, or x to the 1/2 if you prefer. What's g prime of x going to be if we were to just differentiate our outer function?
Half x to the negative 1/2.
Yeah, we use the power rule on x to the 1/2 up here. We're going to get 1/2 x to the negative 1/2, which is the same as 1 divided by 2 square root of x. How about h prime of x? Our h of x is x squared minus 6x. When?
2x minus 6.
Yeah, use the power rule on each term and subtract will give us 2x minus 6. So now I think we're ready to use the chain rule here in order to actually find the derivative of f of x as a whole. Because the chain rule gives us a way to take the derivative of this whole expression, square root of x squared minus 6x, sort of by using the derivatives of the individual pieces, by using g prime and h prime. So if we plug this in to the chain rule, we're going to get that f prime of x is g prime of h of x times h prime of x. So our h of x is x squared minus 6x. So we're going to get g prime of x squared minus 6x. Our h prime of x is this 2x minus 6 term. So here I'm just replacing h prime of x and h of x in this formula with the expressions we already have. H of x was just our original inner function. H prime of x was the derivative of that, the 2x minus 6. And now, here's my question. If we know what g prime of x is. G prime of x by itself is just 1 over 2 square root of x. Here, we're not going to be taking g prime of x, though, when we use the chain rule. We want to be taking g prime of x squared minus 6x. So what would we get if we replaced our x in this formula with an x squared minus 6x?
Are we back where we started?
Well, how so?
Because you'd have a square root of x squared minus 6x. So,
Yeah, we'd end up with that, but this time in our denominator. And so I think what we would end up with is 1 divided by 2 square root of x squared minus 6x. Because when we take g prime of an expression like x squared minus 6x, we're looking at our formula for g prime of just x by itself, and anywhere we see an x in our g prime of x formula, so namely right here, we're going to replace that x with x squared minus 6x. Sort of like back in standard 4, when if we had a function like f of x equals, I don't know, x squared, and I asked you to take f of x plus h, you had to replace any x's that you saw with x plus h terms to get x plus h quantity squared. The same sort of thing is happening here, where if we're taking g prime of some expression, like x squared minus 6x, we go to our formula for just g prime of plain old x by itself, and we're just going to replace this x with x squared minus 6x. And then we can combine these two expressions. We'll get something like 2x minus 6 over 2 square root of x squared minus 6x. And then we can cancel out a factor of 2 from the top and bottom to get x minus 3 over square root of x squared minus 6x. So the moral of the story is, anytime you see a function like this, where you have an inside function, x squared minus 6x in this case, and an outside function, square root of x, both of which were things we knew how to differentiate individually, because you all found with this g of x and h of x, our outer and inner functions, what the derivative of each one was. We can use the chain rule to sort of combine the derivatives for our inside and outside functions in order to get the derivative of this whole conglomeration. Any questions or comments about that? If you're feeling very lost, don't worry, we're going to do some more examples. First though, before we hop into our next example, I'm going to take a quick look at how is this going to be different if we use Leibniz's notation as opposed to Newton's notation. Because we're going to end up getting a formula that looks a little bit different from this, but ends up behaving very similarly. Because if we use Leibniz's version of the chain rule, what we can say is that if f is a function of some other variable u, and u is a function of x, then the derivative of f with respect to x is going to be the derivative of f with respect to u times the derivative of u with respect to x. Looks sort of like fractions almost, in that you can cancel out du in the top and bottom and end up with just a df dx back at the end. So let's see what this means, because this one's, I think, is also a little bit confusing to look at, in that it's like saying, if we rewrite f as a function of u instead of x, there's no u's to begin with, so we need to kind of find a way to sneakily rewrite our function. So for this particular function, f of x, I'm going to claim that f of x is equal to square root of u, where u is going to be some other function, some other expression. And what would u have to be equal to here in order for f of x to be equal to the square root of that u? Yeah?
X squared minus 6x.
Yeah, we could say that if u is just equal to the expression x squared minus 6x, then square root of that u will give us the original function, square root of x squared minus 6x, because we can just replace this u here with our x expression, x squared minus 6x, and that'll give us back the original function. Oops, sorry, this should say f of u now. And here's the kicker. F of u is equal to square root of u. So using Leibniz's notation, what would df du be? In other words, if we treat this as a function in terms of u and take the derivative with respect to u, what would the derivative with respect to u be of u to the 1/2 power? Rachel?
Be 1/2 u to the negative 1/2.
Yeah, just use the power rule on u to the 1/2. Or 1 over 2 square root of u, if you prefer. How about our du dx? If u is equal to x squared minus 6x, if we take the derivative of this u expression with respect to the variable x, what's that going to give us? Don't worry, this one's not a trick question.
2x minus 6.
Yeah, 2x minus 6 again. And so now, if we want to take the derivative of f of x with respect to x, we can take the original function and say that df dx, the derivative of our function f with respect to x, is going to be taking df du, the derivative of f with respect to u, times the derivative of u with respect to x. So df dx here, in this case, will be df du times du dx, which is going to be 1 over 2 square root of u times the expression 2x minus 6, which we combine will give us x minus 3 divided by square root of u. I think there's one more thing we need to do, though, before we can say we've successfully taken the derivative here. Rachel, any ideas?
Do we have to like resubstitute x squared minus 6x for u?
Yeah, I think so. Because right now we have our formula for the derivative, df dx, or f prime of x, is an expression that has x's and u's in it. We'd like to be able to just say the derivative of this is just some expression with x's in it. And so what Rachel suggested is that we have some way to write u in terms of x. Let's substitute that back in here and get x minus 3 over square root of x squared minus 6x, which is the same derivative that we started with. Or the same derivative we got using the other version of the chain rule, which was Newton's method. So this may look very different, but if you look back at the steps we actually did, we essentially did the same thing that we did using the other method. When we wrote out this, that f of u equals square root of u, if u equals x squared minus 6x, that's essentially the same thing as saying square root is our outside function, and the u, in this case, is our inside function. Here, we're just writing it as another variable u instead of h of x. And then when we take df du is really the same thing as our g prime of h of x from the original version of the chain rule. We get this 1 over 2 square root of u, where we're just swapping out h of x with u here. So this is the same as g prime of u, 1 over 2 square root of u. Whereas our du dx is really the same thing as our h prime of x, the derivative of our inner function, so to speak. And so that when we multiply these together, it's in essence the same as multiplying the g prime of h of x and the h prime of x terms together. Yes?
I just want to double check. You said that we might have to do this method on a test or quiz. Like you might specify, or can we always choose?
You can always choose. I'm personally a bigger fan of Newton's method. We are in standard 22, 21, 22, a very late standard, we're going to have to do this sort of U-Substitution technique in order to help us integrate some stuff. But for now, I thought I'd introduce it in case you'd seen this method before, and I wanted to kind of compare. In essence, this method is translating from a different language. We start in the language of x's, and we use the language of u's in the middle of the problem before translating back to x's in the end. It would be like if I were to start a conversation with you all and say, all right, we're going to talk about x's, but now I'm going to speak another language, the language of u's, and all of a sudden, and 2x minus 6. No, not equal to 1/2 u to the negative 1/2 equals 1 over 2 square root of u. We'll translate back into the language of x's again to get x minus 3 over square root of x squared minus 6x.
Gotcha.
That make perfect sense, Zach? I don't know. I figured the language of u should have a lot of ooh and blue blue blues type sounds, so maybe that's just me. Sorry, I needed something to break it up because chain rule I know is a tough one, probably the toughest rule of the lot for taking derivatives. Let's do one more example together as a class, and then I'll give you all some time to work on a few practice problems. Let's say we have a function, so I'm going to be on the third page now. F of x equals x cubed plus 1 raised to the 20th power. Now, if you wanted to differentiate this, you theoretically could using standard 6 techniques by writing this out as x cubed plus 1 times x cubed plus 1 times x cubed plus 1 20 times, and then using the product rule 19 times. Let's not. So anyway, if you do that for me, and you can show your work, I will give you a bonus standard 6 mastery.
Right now?
No. I don't want to do it right now.
I'll try.
Okay, enough. Sorry I mentioned it. Let's see what happens if we use the chain rule. So I'm going to use Newton's approach to using the chain rule on this one. So looks like we're doing two different things here. We have some polynomial, and we're taking something to the 20th power. What's going to be our inner function here, our h of x? In other words, if you were to plug in something for x, if I were to ask you what's f of negative 3, what's the first thing you're going to do to that x? Are you going to take it to the 20th power, or are you going to cube it and add 1 to it? Cube it and add 1? Win? Do you agree? Yeah, I would agree. Because if I were to ask you to plug something in for x here, you're going to cube it and add 1, and then take whatever you get from that and take that to the 20th power. So I think our h of x here will be x cubed plus 1. What's our g of x going to be? In other words, after we take x cubed plus 1, what's kind of our last step in order to evaluating f of x? Please?
X to the 20th.
Yeah, that's exactly it. we take whatever we get from this expression and then take that raised to the 20th power. Because if we take x cubed plus 1 and then we plug that into our g of x formula, that's going to make f of x equal to g of h of x. We take x cubed plus 1, and then we plug that in for x into this expression to get x cubed plus 1 all raised to the 20th power. So now, we can use our chain rule formula that g prime of h of x times h prime of x. Oh, I guess we need our derivatives of these first. Oh, let's see. Who should I pick on? Danielle. What would we get if we differentiated our g of x here?
20x to the 19th.
Yeah. That one I think is just use the power rule on x to the 20th to get 20 times x to the 19th. Ryan, how about h prime of x?
3x squared.
3x squared, and then the plus 1 goes to 0. So our f of x is hard to differentiate because we have multiple moving pieces, but Daniel and Ryan, the two of you handled the derivatives of each of the individual pieces like pros. Tell how pro-like you feel. Because now we can actually take our g prime of h of x, so g prime of x cubed plus 1, multiply it by our h prime of x, which is 3x squared. What are we going to get if we take g prime of x cubed plus 1? In other words, if anywhere that we see an x in our g of x formula, if we replace that x with x cubed, or sorry, not g of x, g prime formula, anywhere that we see an x in this formula, if we replace that x with an x cubed plus 1, what's that going to give us? Right? 20 times x cubed plus 1 raised to the 19th. I like it. You took this x and you just replaced that x in parentheses with our h of x expression, which was x cubed plus 1. So we have 20 times x cubed plus 1 to the 19th, and all of that times 3x squared. And we can combine these then to get something like 60x squared times x cubed plus 1, all raised to the 19th. What do y'all think? Should we simplify this by multiplying out x cubed plus 1 to the 19th? Joseph, you're a fan? Oh, Elise, I think I see you nodding.
I'm a fan of the simplifying, not a fan of the...
Not a fan of the multiplying this out 19 times. I like simple things. If we multiply this out, we're going to have like 20 different terms added up, and it'll take like an entire board to write it out. If you're all good with this, I'm good with this. Yes, Rachel.
Are the answers always going to look that gross?
What, like this? You think this is gross? What makes it gross?
There's just, I don't know, just so much more.
There's a lot going on, and unfortunately, the answer is usually going to be something like, yes, the answers are going to have a lot of moving pieces to them. Mainly because anytime you use the chain rule, you're always going to be multiplying two expressions together, and this one in particular can sometimes end up coming out a little bit icky looking. Like in this case, 20 times x cubed plus 1 all raised to the 19th. Now, on a quiz or something, I would never make you multiply this out. That would just be You want gross, try multiplying this out, and then it gets quite disgusting, I'll put it. I'd say something like this, though, is kind of complicated. It's a more scary looking answer than what we've been getting as answers on our past few standards. And that's why I introduced the chain rule last, because I think product and quotient rules are harder than just the power rule to use. In my opinion, the chain rule is a bit more messy than just the product and quotient rules. So unfortunately, yes, our answers are oftentimes going to be that messy. I can hear some of you all thinking, maybe if you've taken a calculus course before, some of you are thinking out there, Dr. Gerstle, I know how to use the chain rule. If f of x equals x cubed plus 1 raised to the 20th, I know that I can just pull down the 20 using the power rule like this, subtract 1 from the exponent because that's what the power rule tells me, and then I just need to remember to multiply by the derivative of the inside, and that would give me the same answer, 60x squared times x cubed plus 1 raised to the 19th. If you feel like you understand what's going on and you are ready to take your chain rule skills to another level, you do not necessarily have to write out the g of x and the h of x and go through these steps each time. Because in essence, all that we're really doing is we have an inner piece, x cubed plus 1. We have an outer piece, which is taking that thing to the 20th power. If we know to multiply, to do the derivative of this outside piece, which is derivative of thing to 20th power is 20 times thing to 19th power. And then just remember to multiply by the derivative of the thing. So 3x squared here being the derivative of x cubed plus 1. Then you don't necessarily have to go out and do each step where we write g of x equals x to the 20th, h of x equals x cubed plus 1. If this was a quiz question and you felt confident in going right to this step here, you can do so. I introduced this method with g of x's and h of x's because I think the first few times that you do the chain rule, it might be easier to break it up like this. But if you feel like it's easier to just remember derivative of outside piece, leaving the inside alone, and then multiply by derivative of inside, you have my blessing to do that. Just remember that there's a reason why I call this the pro method, because you kind of have to do a lot more in your head. Whereas here, we have all these pieces that we can just plug into this formula, and it's a little less to keep track of all in a single step, I would say. Any questions or comments? All right. See what you can make of the other functions on this page. If you have some time, the next page. There are a bunch of functions that if you want to differentiate, you're going to need to use the chain rule. Go ahead and take a few minutes and see if you can differentiate each of those. As always, you're welcome to talk to your neighbors or flag me down if you have any questions.
For this one, you could use the quotient rule and use the chain rule for this.
Indeed, that one's a nasty one.
All right, just make sure.
Yeah, that one does require chain rule inside of quotient. The ones on the next page are harder than the ones on this page. You might need to combine chain rule with some other rules we've looked at. could, or I think this one you could do either use the quotient rule on this, or you could just rewrite this expression as a single, something like 5 minus 3x squared to the negative 4. And then avoid having to use the chain rule necessarily on it. Or, sorry, you need to use the chain rule, but you can avoid using the quotient rule that way. Right, here's the chapter sheet. Let's see if you can find a 4. That's a scary one, that's why it would be mean if you want like that on table. But I want you to try at least one table. So use everything you've learned in this type of problem. I would say if there's some easy way to simplify that doesn't involve doing nasty things, I encourage it. You're not required to. Let me help you. Like here, for instance, you can combine the one half and negative I t. That's what I would do, at least if I were doing this problem.
Yeah, that's right.
Combine the simple
These are the
things
fines.
and then leave the more scary, complicated things you can move along.
Yeah, that's fine, that's right. You can't simplify that. I mean, it would be a lot of work. That'll simplify.
Start.
The angle square root is super easy. So it's always gonna be just 2x. So it's gonna be the square root, just move to the side plus 2. Since there's 2 here, you just cancel it out, so it's just 2x.
Once you get to the point where you've taken the derivative of square root 100 times,
Yeah, it's,
I just start thinking of, which I have, I just start thinking of it as, oh, okay, that's just 1 over 2 square root, rather than
Yeah.
having to think about, all right, let's rewrite this as x to the 1/2, and then 1 x to the negative 1/2, which is 1 over 2 square root.
yeah.
Yeah, if you feel good about your way to skip that without writing it as a fractional exponent in between, go for it. Okay, we're almost out of time for today, so I want to make a couple announcements before the end of class. I encourage you to try and finish the rest of this page, maybe over the weekend, see what you can make of it, and then on Monday, we'll look at a couple of these problems together as a class and see what you all came up with. But just so you know, I also plan on Monday to start Standard 8. And Standards 5, 6, and 7, we've talked about a bunch of derivative taking techniques for a variety of different types of functions. But one thing we haven't done yet is to talk about what happens if we have a graph of something that's not actually a function, like a circle. In Standard 8, we're going to talk about how you can differentiate things that are not actually functions.
Big brain.
Like how to find slopes of points on a circle. Okay, hope you all have a good weekend. I will see you all on Monday.